Support for Design Matters Media is provided by Wix.com, which puts the creative power of building dynamic websites back into the hands of designers. As anyone who has spent time in a WYSIWYG platform knows, what you see isn't necessarily always what you get. On the flip side, for some, it's far too easy to get lost in code and lose the forest for the trees. Wix.com allows you to find your own personal sweet spot and take control of your site with their drag-and-drop editor, hundreds of advanced design features such as Retina-ready image galleries, custom font sets, HD video, and parallax scrolling effects, and even serverless, hassle-free coding for robust websites and applications. With Wix.com, you have total control of your web design like never before. So join Wix's brilliant community of designers, artists, and creatives at large around the world for free. And ask yourself, what will you create today?
This is Design Matters with Debbie Millman from DesignObserver.com. For 14 years now, Debbie Millman has been talking with designers and other creative types about what they do, how they got to be who they are, and what they're thinking about. On this podcast, Debbie Millman talks with astrophysicist David Spergel about the universe and about his career.
Luck is one of the most important things a scientist can have. You can have bad luck and the rocket could explode. So lots of stuff can go wrong.
Here's Debbie Millman.
David Spergel is a theoretical astrophysicist. His research interests range from the search for planets around nearby stars to the shape of the universe. He's a MacArthur Fellow, a professor at Princeton, and the director of the Center for Computational Astrophysics at the Flatiron Institute in Manhattan. Now, normally on Design Matters, I talk to writers and designers and other creative people. Science isn't always thought of as a creative process, but the universe is so unbelievably glorious and strange. It takes someone who is highly imaginative to even begin to understand it, and then be able to communicate their understanding to the rest of us. Spergel joins me to talk about what he does, what he's thinking about, and the composition and origins of the universe. David Spergel, welcome to Design Matters.
Thank you. It's a pleasure to be here.
David, you recently won one of science's highest honors, the 2018 Breakthrough Prize in Fundamental Physics. Congratulations.
Thank you.
The prize was created by the founders of Google, Facebook, Alibaba, and more, and you were given the award for your work mapping the cosmic microwave background, the earliest, oldest light we can detect from the universe's infancy. But what was with the tie you wore on the red carpet? Did you really wear a bow tie made of feathers?
Turkey feathers.
Turkey feathers. Tell us the story.
I had been in Washington, D.C. the year before. Forget the name. There's an art museum right across from the White House.
Okay.
And in the shop, they had these beautiful bow ties made of turkey feathers. And I had never seen anything like it before, and I decided to splurge and get one. I didn't really think of myself as a bow tie person, but it looked good. And then I decided for this award that I would buy a new bow tie. And I went on the web, and I got an orange and black bow tie. And it was my sort of little tribute to Princeton, who had supported my research for 30 years, to wear a bow tie in the school colors. And I thought it was, I don't know if subtle was the right word for an orange and black bow tie.
Made of feathers.
But it was a fun thing to do.
Yeah, absolutely dapper and very risky. Very fashion risky. And congratulations on that as well. You were born in Rochester, New York, where your father was a graduate student studying particle physics. Yet you moved to Huntington, New York, where you were raised. Mm-hmm. Why Long Island?
My dad went to work for Grumman Aerospace.
That's the whole story?
I was too. I really had, limited input.
Family history, a little bit of anecdote, nothing else. You got nothing for me here?
I got nothing for you.
Okay.
I had limited input into the decision to move at age 2. I grew up in Comac initially, which is one part of Huntington. And when I was 13, one day I came home and my parents announced, we're moving to a brand new place. And we moved not that many miles, but brand new school, brand new people.
Was it traumatic for you?
I think in retrospect, it was a good change. Right? I've ended up finding a niche and friends, and it worked well.
Your father worked on the Apollo project and cosmic rays, and he was also the head of science at your college. When did your interest in science and astronomy first take hold?
Yeah, so this is where I get really boring, right? Because I was interested in science really early on. I was exposed to it through my dad. I was someone who was good at math and things like that. And I think if you asked me what I wanted to do, I would have guessed something like this, at age 10. I've sort of been on this path for a while.
I know for a fact that you had other interests as we first met many, many years ago back on Long Island. As, dear listeners, David and I went to high school together. I knew him when he looked like a character out of the TV show Big Bang Theory, and I had a bad version of Farrah Fawcett hair. David, who would have thought we'd have ended up here?
We're both at a better place now.
I think so, too. At least
fashion-wise.
Between your turkey feathers and my better hair, right? I was looking through our yearbook from John Glenn High School in 1978. You were voted class intellect, and that was well-deserved. I was voted class dramatist. A lot good that did me. But back in 1978, you were a senior at John Glenn High School, and you participated in the intense Westinghouse science talent search for students who, quote, dedicate countless hours to original research projects and write up their results in reports that resemble graduate school thesis. Your project was on the rings of Uranus. How did you do in the contest?
I think I got an honorable mention. I think the project showed reasonable taste. The rings of Uranus were just discovered, and I knew that the rings of Saturn were affected by the moons of Saturn. So I thought, I'll figure out if the moons of Uranus affect the rings. And
how did you go about doing that back then?
I wrote a computer program, right? And this is not a computer program written on cards, because while people wrote cards then, our high school didn't have anything that sophisticated. Okay. So it was written on paper tape, which was a really ancient technology. And the problem with the work, kind of like looking back on it later, was I didn't understand the right way to evolve orbits. So what I found was if you put a particle in the ring that was in a space between the rings, it would shoot off and be unstable. What I didn't know to do was to run the orbits without the moons. I would have gotten the same answer. The numerical integrator I used, because I invented one, not knowing the whole field was there, was violently unstable.
How did you create this device in the first place?
I wrote some computer code. I had taught myself, I think, BASIC, and wrote a code, some program in BASIC to do this.
So in 1978, you were writing your own code.
I was writing my own code.
How did you learn how to do this? There wasn't classes for this in John Glenn High School.
There was books and things. I think I learned it from the library, so I looked up what to do and wrote it. In fact, because what I did has this basic mistake, when I teach programming and scientific programming to undergraduates, one of the first assignments is to reproduce my high school project and show why it's wrong.
Fantastic. And do most people figure it out?
Yes. I now understand if you're going to do a calculation or a simulation on the computer, you first need to show that your program isn't producing nonsense. This is a problem. A lot of people believe what comes out of a computer. So what we know is if you put a planet like the Earth on a circular orbit, it should stay on the circular orbit. Most of us have noticed the Earth has kept going around the sun at about the same distance all our lives. And so we probably believe that scientists have known that it's been about in the same place for billions of years. So if you write a computer code that tells you that the Earth wanders off and its orbit changes on the timescale of a couple years, there's something wrong with your program.
I get it.
And that was the mistake I made with this project. So looking back on that 17-year-old me, good ambition, good taste, needed some training, needed to learn some stuff.
When you got to Princeton, you selected physics as your major, dubbing it, and I quote, really exciting. I read that attending the Woodrow Wilson School of Public and International Affairs was your second choice, your close second choice. What influenced your decision to abandon that choice and ultimately pursue physics?
I've always wanted to do something that was politically relevant. I've always been fascinated by politics. I'm actually now quite active in science politics. And I think I didn't so much abandon the Woodrow Wilson School, but got drawn into astronomy. I had the opportunity to do research my junior year with two terrific faculty. There's a visiting professor from Oxford who gave me this problem, actually studying orbits, going back to my high school project, but now doing this in a very deep way mathematically. And I really loved learning this sort of the mathematical elegance of the orbits. Do you remember this thing when you were a kid called spirograph?
Yes. I still have one.
And what we were able to show my junior year was you could decompose the orbit of a star moving around the galaxy into two different spirograph pieces. And that mathematical representation where you could basically describe a star in terms of the three spirograph pieces that you need to trace its orbit over the billions of years. That mathematical elegance of the underlying properties of the universe, to me, was really compelling.
David, what makes something mathematically elegant?
I think it's actually a question that what makes a design elegant?
Well, I could talk about the golden ratio. I can talk about symmetry. I can talk about kerning. There's a lot of different elements that go into making something pleasing to the eye or beautiful. But what would make something elegant?
Symmetry is this incredibly powerful concept in physics. It turns out that the laws of nature are highly symmetric. Some in ways we're very familiar with. There's no real difference between whether the wind is blowing this way or this way, left or right, up or down. Gravity works the same, doesn't have a preferred direction. There's no preferred direction in the universe. There's no preferred orientation. There's no preferred spot in the universe. That's one kind of symmetry.
And are we sure about that?
We try testing it, and consistent with all of our observational tests, that's what we see. We also observe that the mathematics that describes, say, electricity and magnetism are the same equations that describe electricity and describe magnetism. Only you take the equations and you rotate them slightly. You do a mathematical rotation and changes one to the other. We notice that the proton and neutron are very similar, except for just a slight change of symmetry. And this principle of symmetry has driven the way we've understood fundamental physics. And one of the things we don't understand about the universe is why it's so simple, why it's so symmetric, why our concepts of mathematical elegance actually seem to guide us towards a deeper understanding of the underlying physics.
As a theoretical astrophysicist, do you have any sense of why that is? Any hypothesis?
No.
Damn.
So, this is one of the most profound things about the universe, that it is so simple and so elegant. And we don't understand, why is that so? And you can think about this from the science that we're familiar with. You look at all the stuff that makes up the room around you. It's really complicated stuff. But in the end, it's all made up of atoms. And everything we see are made up of 100 different types of atoms. So that's pretty simple, that everything comes down to 100 building blocks. But then you look at the atoms, and they're just made of protons and neutrons and electrons. So basically 3 things make up everything.
But those protons, electrons, and neutrons are also made up of things.
Right. But again, as the deeper you go, the simpler it gets. Why is that true? We don't know. But this sort of principle of simplicity and symmetry has been a very important guide for our developing our understanding of theoretical physics.
When you began your first study of the millimeter sky, you had a focus on modeling the galaxy rather than the cosmic background radiation. At that time, your work showed that the Milky Way is a barred galaxy. What does that mean?
So the Milky Way is our galaxy. It's where
Yes.
we live. It's made up of billions of stars. A star like our sun lives in a disk. So you can think of the sun as in a disk of stars rotating around. We've done about 200 orbits in the 10 billion year history of our galaxy. And we've got this disk where we are. We're about 24,000 light years out, 8,000 parsecs. As you go further in, the stars arrange themselves basically into a shape that looks like a watermelon or a football. And we call that a bar.
Okay.
And in some ways, it's easier to study other galaxies than our own. Because we live in our own galaxy. And it's
Are we tainted by our own observations?
In some ways, in the sense of, we don't know what the back of our own heads look like, unless you have mirrors or someone shows you. It's much easier in some ways to observe others and see what they look like. With our own galaxy, because we're embedded in it, our view of the galaxy is actually blocked by dust. Dust has been the bane of astronomy in some ways and has led to confusions many times. The first confusion came back in the 1800s when we started counting the stars around us. And we concluded from this that we were in the center of the universe because there were roughly equal numbers of stars in all directions. What we didn't realize was the reason we didn't see more stars in the direction towards the center of our own galaxy was because there's dust in our galaxy that absorbs light and blocks our view of the stars. So that because of this dust, it's hard to see what our galaxy looks like. Now, this dust absorbs optical light, but it's not so good at absorbing infrared light. And what we used in this work was there had been recent observations that NASA had made with a satellite called COBE that made a map of our galaxy in the infrared.
And COBE is the Cosmic Background Explorers.
Yep. When you look at our galaxy, you notice if you look at the infrared that one side is brighter than the other. And that's because that side is closer to us than the other. But think about that watermelon. And this part of the watermelon that's closer to you looks brighter. So what I ended up doing with a colleague was we made basically a pretty simple calculation of what is it like to observe a watermelon in space.
Really? An actual watermelon?
A watermelon-shaped structure of stars.
Okay.
But a watermelon would give you the same answer.
Okay.
And showed that was a good match to the data. And that became a big part of our convincing people that the Milky Way is a barred galaxy.
One of your crowning achievements is your work with NASA's Wilkinson Microwave Anisotropy Probe, known by the acronym, mercifully, WMAP. The WMAP satellite launched in 2001, and it captured images of microwave radiation left over from the Big Bang. You studied this radiation, the oldest light in the universe, and shared what you've described as a baby picture of the cosmos with the world. You and your team were able to pin down the age of the universe, nearly 13.7 billion years old. You also calculated that the universe is made up of 71.4% dark energy, 24% dark matter, and a mere 4.6% ordinary matter. Astrophysicist John Bacall said this about that work. It's a rite of passage for cosmology from speculation to precision science, and added that astronomers would remember where they were when they heard the announcement. How did your life change at that point?
Well, the period of time leading up to that announcement was one of the most demanding.
Yeah, sleep is for the week T-shirts you gave your
That's
team.
right.
How mean.
They all treasured
Taskmaster,
them.
yes.
At the time I had 3 kids, including an infant. So that was demanding as well. And we had the responsibility of analyzing this data, which wonderful data, and building a model from this. So I never worked harder than I did at that time.
Did you have a sense that you were onto something big? Did you have an intuition that this was...
It was clear that the data was great. It was telling us important things. We were working with a really small team.
So let's deconstruct this a little bit for the layman. So you're like out walking, taking a run, doing something that gets your brain moving. And as a theoretical astrophysicist, you have to come up with theories that you then can test. So when did it come to you that there might be this leftover radiation that would be measurable?
Oh, so the idea that there was leftover radiation was known. So this was discovered by Penzias and Wilson at Bell Labs back in 1965. They won the Nobel Prize for that. The fact that the universe is filled with this leftover heat from the Big Bang is the basis of the Big Bang theory at this point, hot Big Bang theory.
Which at one point, or for quite a long time, people thought was kind of magic.
Right. We expected there would be fluctuations because if the universe started out completely uniform, it would stay completely uniform. And since we're here, the universe isn't uniform.
Right.
We see stars, we see galaxies, so they had to come from somewhere. And that meant we expected fluctuations to be there.
Now, I want to read a paragraph from a really marvelous book titled Echo of the Big Bang by Michael D. Lemonick. And it's something that I'm going to conclude with a one-word question, okay? So this is from his book. The fact that this background glow of cosmic microwaves existed at all was powerful evidence that the Big Bang had taken place, an unmistakable announcement that the universe had a birth date. But theorists quickly realized that it could also be used as a powerful diagnostic tool. The modern universe, they knew, is lumpy, mostly empty space, punctuated at varying levels of organization by stars, galaxies, clusters, and superclusters of galaxies. These lumps must have started as variations in density in the newborn universe, which grew under gravity into their present form. But since the newly found glow of microwaves was emitted when the universe was a mere 300,000 or so years old, any density variations present at the time should have left their imprint on it. A slightly overdense region would have been very slightly hotter than average, while slightly underdense regions would have been cooler. And these temperature differences should still be detectable even after 14 billion years. So my question, David, is why?
It's because microwaves don't interact much. So to explain this, let me give you a little background, teach everyone a little special relativity.
Excellent.
The key idea in special relativity is light travels at a finite speed. It takes light 8 minutes to get from the sun to us, so we see the sun as it was 8 minutes ago. Look at a nearby star that is, say, 10 light years away. It takes light 10 years to get from there to us. We see it as it was 10 years ago.
10 light years.
10 light years. So the further away something is, the longer it takes light to get to us, the further back we look in time when we see it. So we see the Andromeda galaxy as it was 1 million years ago. We look with the Hubble telescope, we see the light as it was, say, 12 billion years ago for a distant galaxy. Microwaves are the oldest light. It's been traveling to us for 13.8 billion years. And what's important about these microwaves, well, first, they were generated back then, but this radiation doesn't interact much with ordinary matter. It doesn't interact much with electrons. Now, that means it basically comes to us unaffected. I think of it a bit like it's a cloudy day, you look out at the clouds, you get to look through the air and see the surface of the clouds. And that's the image you should have. We're looking out in space, same way we'd look out in a cloudy day, looking back to see the surface of the universe at this point 300,000 years after the Big Bang.
So pretty much at the beginning of time.
Close to the beginning. And what makes that data wonderful, and this is sort of what got me going on this whole project, was the universe back then was really simple. And because it was so simple, relatively simple mathematical models could be used to understand it. So that if we could make precise measurements, we would be able to interpret those measurements in ways in which we could draw really big conclusions, things like the age of the universe and its composition.
George Smoot, the principal investigator on one of the Cosmic Background Explorer's key instruments, declared at the time that it was like seeing God. How do you feel about that?
I think what George meant was there's a Greek word epiphany. right, which means to see the face of God. But people use epiphany to be that moment in which you see something new with great clarity. And I think that's what George was trying to say. Not that this is telling us something about the nature of whether there's a creator or not. That's a question I think we need to approach with some humility. But I think he wanted to convey the real sense of excitement and inspiration. And it's a moment where the universe comes to you and you realize it has told you something about the way it works. And that is something that's a really special thing to have been fortunate enough to experience, that you could realize that you were the first person to be able to measure these properties of the universe.
You've been able to outline the first seconds of the universe, the creation of everything, when space, time, matter, and energy burst into existence. Do you have any sense of what happened, or if anything could have happened or existed before the Big Bang?
That's a really good question. What was there before the Big Bang, or is there a before the Big Bang? Broadly, we have three possible answers that people have been exploring. One answer is, well, before the Big Bang, maybe before the universe was expanding, it was collapsing. So the universe went through a stage of collapsing to a very high density, bouncing and re-expanding.
So we're just sort of a recycled...
That's sort of the recycling model.
A recycled universe.
Or, it's a model that's like a lot of models from Eastern philosophy of the history of the universe, where the universe is created and destroyed and created and destroyed repeatedly. There's a second model that basically says the universe, there is no before the Big Bang. The universe, time itself begins with the Big Bang. And to ask the question, what's before the Big Bang, is like asking the question, what's north of the North Pole? There is nothing north of the North Pole. That's when time begins, and the universe emerges at that point. Another way people think about this is they imagine the universe emerging from a quantum foam.
From quantum foam?
Yeah. But fundamentally, this is a question that we don't have the physics tools to answer. There are two great ideas in 20th century physics: general relativity and quantum mechanics. And they both work remarkably well.
But they don't work together.
They don't work together, and we need to figure out how they work together before we can answer this question, what was there before the Big Bang, or was there before the Big Bang?
If there was a before the Big Bang, do you think there would be any evidence of that in any type of wave or light or energy?
Possibly. So there are some models that people have developed of what might be there before the Big Bang that made predictions on what we would see in the microwave background. So one of the wonderful things about, say, the microwave background is we really are seeing the universe's baby picture. Sometimes you could learn something about a baby's conception from the baby picture. Was that really the father? Questions like that. In our case, what we were looking for were statistical properties of the fluctuations. And if you look at the pattern in the microwave background, you see a mixture of hot and cold spots. And one of the basic symmetries you can ask is, are the hot spots the same as the cold spots? If I take my picture in which the hot spots are red and the cold spots are blue, and I switch my color scheme, does the picture look the same? That symmetry between switching plus to minus would have been broken in some of these models in which there was a pre-Big Bang bounce.
And so your sense is that there likely wasn't?
Well, we didn't see it.
Okay.
But that's only one possible prediction, one possible way to do that. We don't have robust models. This is a question I'm fascinated by, but it's not a question that I have a solid answer. I like to distinguish between things where I have some confidence that what we're saying today might be how we view things 10 years from now, 20 years from now, 50 years from now. So the idea that the universe is 13.7 to 13.8 billion years, we actually have a pretty robust measurement of that.
And the universe has been expanding for that whole time?
That whole time, yeah.
What is the universe expanding into?
The future.
So does the future already exist? Is there a void or a vacuum that we are filling up?
Well, most of us have sort of a Galilean notion of space and time. It comes back to Galileo, where space is something that's absolute, that you have to expand into. What Einstein taught us is that space is relative. There is no absolute distances between objects. You can only measure relative distances, how long it takes light to move from me to you, how long it takes light to go from a nearby star to us. So we can just measure relative distances, and the relative distance between objects are growing. So the universe actually, while it's expanding, so the distance between objects are growing, it's expanding everywhere. It's not expanding into anything.
But there's to be room for it to move.
Right. Space can grow, creating more volume without expanding into anything in 3 dimensions. If you think about things 4-dimensionally, that's why I wasn't being facetious by saying it's expanding into the future. In the future, there's more volume to space. So that space is always growing and growing. Now, we can turn that picture around. If we're expanding into the future, in the past, things were closer together. And the picture I have of the Big Bang is I think of a balloon, and we're living on the surface of the balloon. And that's a 2-dimensional picture. We get to live on a 2-dimensional surface rather than a 3-dimensional universe. The radius of the balloon is time. So as we go into the future, the balloon gets bigger and bigger. The volume of space grows. There's more surface area to the balloon. Now let's run time backwards. The balloon collapses down, eventually collapses down to a point. A whole balloon comes together. That's the moment of the Big Bang.
The singularity.
That's the singularity. Now you'll notice there's no special place on the balloon. Every place on the balloon collapses down to that central point. The Big Bang didn't happen in a little town in Ohio or in that distant galaxy. It happened everywhere. Everywhere on that balloon shrinks down to the same point.
Your measurement supported a so-called flat universe dominated by dark energy, this mysterious force that pushes this universe we're in apart. And the data also supported the theory of cosmic inflation, a hypothesized exponential expansion of space-time immediately following the Big Bang. And these measurements led to the establishment of the standard model of cosmology. Can you explain the standard model of cosmology?
I think of the standard model of cosmology beginning with the observation that the universe is remarkably simple and remarkably strange. Remarkably simple in that a very simple model describes the geometry of the universe. The geometry that we learned in John Glenn High School. The sum
Mrs.
of the
O'Brien.
Yep.
Hi, Mrs. O'Brien.
Actually, not even from Mrs. O'Brien, because Mrs. O'Brien taught calculus.
And trig. Yeah.
But what we learned actually in 9th grade, which was the Elwood Junior High.
Yes. Who did we learn that from?
I don't remember
either. I remember Mr. Margiata, but I don't remember.
I don't remember who taught 9th grade math in Elwood Junior High.
Me either.
Was that the sum of the angles of triangles 180 degrees, that the circumference of a circle is 2 pi r. That mathematics not only was the right answer in 9th grade to the test, it describes the geometry of the universe writ large on scales of billions of light years. What could be simpler? That's, the geometry you write on a piece of paper, a flat piece of paper, works on the scale of the universe. That's what we mean by the geometry being flat. General relativity, we've taught you special relativity.
Yep.
The key idea in general relativity is matter tells space how to curve. And the curvature of space tells matter and light how to move. That's what Johnny Wheeler taught us. And if you ask, what does it mean to say that the geometry is flat, that this, like a piece of paper, the stuff from 9th grade works? It means the total energy of the universe is 0. That the energy in expansion, kinetic energy, exactly balances the gravitational energy of attraction, which is negative. So again, it's the simplest thing it could be. The simplest number to write down is 0, and that's the total energy of the universe. It's also simple in terms of the properties of those fluctuations. There's no special direction, no special place. The fluctuations that grew to form galaxies, they're described by a bell curve, which is the simplest distribution you can have, equal numbers of hot and cold spots. At the end of the day, the millions of observations we've made can be represented entirely in terms of 5 numbers. The age of the universe, the amount of atoms in the universe, the amount of matter in the universe, how lumpy the universe is, and how that lumpiness varies with scale. And with those 5 numbers, I can fit all the data. It can't get simpler in some ways. Well, it could, one way.
How? How?
Well, what's strange about the universe is its composition. Atoms, the stuff that make up us, and you mentioned this already, makes up only 5% of the universe. The remaining 95% is in stuff that we don't understand. We've given it names. We, as scientists, make up names to describe stuff we don't understand. One name we've given for some of the stuff, we call it dark matter.
Which is a terrible name because it's not dark, it's invisible.
Yes.
Okay.
It is invisible matter.
That's been bothering me.
It's gotten better. We used to call it missing matter. And it was missing because you couldn't see it. But
there's too much hubris in that.
We detected it gravitationally. So it's stuff we can feel its gravitational effects, but we don't know what it is. It could be some new particle we haven't seen yet. It could be in the form of black holes. We have arguments why that doesn't work for many mass ranges, but it could be some new tiny light particle we haven't seen before. We just sense it's there gravitationally. My PhD thesis actually involved ways of looking for it. Those haven't worked yet. And that's the stuff that's less strange, the dark matter. The even stranger stuff is what we call the dark energy. There is energy associated with empty space. And general relativity tells us energy affects the way space is curved and how things evolve. So that's how we sense it. And it's strange. There's a tiny amount of energy associated with empty space. And we don't know much about the properties of this. That's actually one of the main focuses of my current research. I'm now involved in a NASA mission that we're designing, hope to launch in 2025, that will, among other things, study the nature of dark energy. And we'd like to see is it staying the same with time? Is it growing in energy? Is it shrinking? The dark energy grows with time. We're in trouble.
Will it overtake us?
It will eventually first tear apart galaxies. Then it will tear apart atoms, and then tear apart nuclei, and then tear apart the structure of space-time itself, and destroy everything in a big rip. So back in the beginning of November 2016, I was asked by a reporter, what I thought about the evidence for the big rip, the idea that the universe will be destroyed in this very rapid expansion. And I said, there might be some data that suggests it. But I felt fundamentally it was like the Trump presidency. This is November 1st, 2016.
Oh, interesting.
I said it was frightening to contemplate, physically possible, but I don't think it's going to happen. So I now look out and think, our universe is going to be destroyed in a big rip.
Now, earlier in our conversation, you said that you have a lot of interest in science politics. What does that mean?
So, I was on the NASA Advisory Council and served as chair of the Space Studies Board, which meant that the job of the National Academy, set up by Abraham Lincoln, is to provide advice to the president and to Congress on scientific questions they ask about. And one of the things that we've been doing in space science for 60 years is every decade we get together as a community of astronomers and we identify what our top priorities should be. So one of the ones that's very famous is we said back in the 1970s and 80s, our top priority should be to build something like the Hubble telescope. And then Congress supported it and spent billions of dollars on it. And over each decade, we identify our top priority and then go to Congress and articulate the case for this. And actually, the system has worked very well. Congress and the White House, regardless of party, have preferred to have the scientific community set its science priorities, then have it set by some political process where what mission gets built, what project gets built is determined by whether or not one scientist happens to have the ear of a politician.
That feels way too arbitrary.
Rather than have this arbitrary politicized system, we've relied on this community process that identifies priorities decadally. And I've been very involved in that process and in implementing it. And it's something that I actually feel really good about. And we started with this in astronomy, and we now do this in planetary science. Congress and the president want to know, is it a higher priority to send the next NASA mission to Mars or Venus or a moon of Jupiter or Saturn. This is not really a Republican-Democratic issue.
No.
And you don't want this decided on whether or not the company that builds the mission to Mars is in the district of a powerful senator. You'd like this decided on scientific grounds. And up to now, it has worked well in that Congress has asked the scientific community what the priorities are, and then NASA works towards those priorities. So that's been the aspect of science politics I've been most involved with.
So much of theoretical astrophysics seems to be calculations. Though you're looking at raw data much of the time, in your mind, can you visualize what you're studying? What does it look like to you?
For me, visualization is really important. So the way I tend to think about data, the way I tend to think about theory is I draw a picture in my mind. I think about particles colliding with each other. For me, the mathematics describes pictures, and I think in pictures, and then develop the math to convey the picture to others in a precise way.
So it starts first as a visual image.
I think different people think differently, but for me, it starts visually. I'm a very visual thinker.
You've said, if at first you don't succeed, try again. But after 3 tries, move on to something else. And you've also described yourself as risk adverse, which is something I did not expect to find in my research. And have stated that you think you have sometimes been too risk averse and have probably missed some opportunities, perhaps intellectually and professionally, by not taking risks. What type of things are you talking about? What kind of regrets do you have?
Let's see, I'll start professionally and then go intellectually. I was very happy at Princeton, but, I stayed at the same job in the same place for 28 years. It was one reason it was just a wonderful environment. But on the other hand, it meant I didn't take on some new challenges. So for the last 2 years, I've been here in New York. I'm spending most of my time running a brand new center.
And that is the Flatiron Institute?
The Flatiron Institute. So I was chair in Princeton for a decade. And I was in the wonderful position of inheriting what was the best theoretical astrophysics department in the country. And my job was to keep it the best. But there's something really exciting to be in a complete startup, to be employee number 1, to get to invent from start how you imagine your institution to work. I hadn't taken on risks like that, starting something new institutionally.
What held you back?
I guess I was happy where I was, and perhaps afraid to give that up. I think this is true for all of us. The things you realize in retrospect. You get thought about something. One of the big choices you have to make as a scientist is, where do you spend your time? And there were things that were risky that could have turned out to be more interesting than I thought they'd be, and I could have gone that way. So looking back, I think I have some regrets like that. That said, I've been really lucky. I've gotten an opportunity to do some really great things and been part of some fabulous projects.
Do you really think that luck has something to do with this, David? You're a scientist.
Oh, I think luck is one of the most important things a scientist can have.
In what way?
When you start out on a research project, you don't know whether it's going to turn out to be interesting. And people sometimes think they have good intuition and they can find the right way forward. And maybe that's part of it. But some of it is luck. You work on a project like the WMAP project. You work really hard, and my colleagues work really hard to make sure the experiment succeeded. But there's always a chance you put a satellite on a big explosive rocket. You can have bad luck and the rocket could explode. And when you're involved with projects that are big projects, political forces beyond your control can kill a project. So lots of stuff can go wrong. But mostly, I think of luck as, you choose to go off in a direction, and that direction turns out to be interesting.
How do you balance the line between risk, hesitation, and knowing when to pull the plug on something? How do you have a sense of when luck is going to show up?
Well, I do think there's an element of which, you make your own luck, right? And I think you want to have an intellectual portfolio of ideas that you're working on, some things that are pretty likely to work out and produce interesting results, but maybe not be huge high reward, but good solid stuff. And to try some things that are riskier and might turn out to be really interesting. Now, most risky novel ideas are wrong. So I think it's really important not to fall too deeply in love with your own ideas and to be willing to listen to others and respond to criticism. And when people raise doubts about what you're doing, to listen to those doubts.
When do you fold? How do you know when to fold?
When your ideas start to become increasingly baroque, when you have to keep making excuses of why things don't really work. So one of the things I worked on when I was younger was an idea called textures.
Cosmic texture.
Cosmic textures. So the idea here was that galaxies and all the structure we see were produced as a product of a phase transition. Now, a phase transition is something like water going to ice. So if you put water in your ice tray and put your ice tray in the freezer, when you do that, it doesn't crystallize perfectly.
You see little bubbles.
You see little bubbles. And there's energy associated with those bubbles. And our idea was that something like that happened in the early universe. And it was those little bubbles that provide the seeds that form galaxies. It's a beautiful idea. All sorts of nice mathematical
It's
features.
very elegant.
Yes. But it doesn't describe the universe we live in.
Right.
And when the data came in from the COBE satellite back in the late 80s, the result came out. I saw it the moment it came out. I looked at it. I knew what our predictions was. And I turned and said, we're dead. And I stopped working on it.
But that work, in your defense here, that work led to your hypothesis about the early universe that ultimately resulted in you getting your MacArthur and what will likely end up resulting in your getting a Nobel Prize. So it's all relative.
No, I mean,
as Einstein would say.
Often wrong ideas point you in right directions, and that this is a good case of it. I'm glad I explored that idea. I'm also glad I stopped exploring that idea.
Yes.
Often you can reduce the number of stumbles by finding friends who could help guide you and teach you things. And that's been a way I've been working a lot.
You still do quite a lot of teaching. You actually have 3 jobs. You're working for NASA, you're running the Flatiron Institute, and you're still running the Department of Astrophysics at Princeton.
I'm no longer chair at Princeton.
Okay.
I am still teaching there and working with a whole bunch of graduate students. So I do have 3 jobs.
Yes. Now, when you started out as an assistant professor, one of your colleagues spoke with British physicist Dennis W. Sciama, who taught Stephen Hawking about how to be a good mentor. And his advice was this: the most important thing you can give a student is love. I think that's actually one of the most beautiful things I've ever read about teaching.
That is a wonderful statement and something I've tried to learn from and apply. You know, he had taught Stephen Hawking, Baron Rees, who was head of the Royal Society, Roger Penrose, a whole slew of important physicists. And he basically said, if you give your students love and the confidence to believe they can do important things, they will find important problems and do important things. And I think this is one of the most important things we can do as teachers, is give our students the confidence to attack important problems. Because it's only when you work on important problems and ask them and try new things that you're going to make real progress.
How do you stay engaged when your knowledge is so much more developed? How do you keep engaged as a teacher?
It's fun to convey the excitement of the universe. One of the things I like about the class I'll be teaching next year, it's called Imagining Other Earths. It's actually a course that I offer, most of it really online, as a Coursera course. It's a free class. I ask the question, is there life elsewhere in the universe? What are the conditions for life? And it's a chance for me both to talk about the physics and astronomy of our galaxy and other stars, stuff, at least at the level of freshman I know well, I feel. But also for me to learn new things and ask questions like, if there are life forms on other planets, what properties would they have? And I think you can argue that they probably have to have a mouth and an anus because they're going to eat. And as the book says, everybody poops. And they're probably going to have eyes because light is one of the most important ways of carrying information. And you want to know what's out there to eat and what's out there that might eat you. And the eyes may be very different in detail. There are photosensitive plants. There are eyes in insects. They've all evolved independently. So if there are indeed aliens, their eyes will look very different, but they will be photosensitive. They could see light. And so it's fun to think about things like that.
Absolutely. I know that you've said that questions such as, are we alone and what is the fate of the universe, are the key questions of our time. Do you think we're alone?
Probably not. But I don't have scientific evidence that answers that question either way. We know there are lots of planets out there now. We don't know whether they host life. We don't know how often life evolves. And if life does evolve, we don't know how often it reaches advanced life forms.
Tell me what you're doing now at the Flatiron Institute. You are now the director of this brand new institute, and you are doing some really significant things. The title that you have at the Flatiron is the director of the Center for Computational Astrophysics.
So advances in computing, and by that I mean not just the fact that computers are bigger and faster, but the fact that advances in computer science and applied math means we have new tools. Let us, I think, make big advances in fields like astrophysics. I think of using the tools in two ways. One, we take the data, and we now have lots of what we would call big data, positions of billions of stars, properties of billions of galaxies, and we apply some of the techniques that people use for things like facial recognition in Facebook to understanding shapes of galaxies. We also use tools from numerical simulation to make simulations of how galaxies form, how planets form, what happens when stars collide or neutron stars collide. And these kinds of simulations require big computational codes. And what we're doing at this institute is we're trying to be at the forefront in developing new techniques and new ideas for these problems. It's a unique place in that we're funded by a private foundation, the Simons Foundation, and have free rein to basically do risky things.
That's wonderful. That's really exciting. So my last question is this. In your field, there's a lot of prediction with sometimes years or decades before either being proven to be true or not. For instance, about 31 years ago, you proposed detecting dark matter wind. And just now, some have begun looking for it. Is there a sense of satisfaction in this idea coming back to life after 31 years, a notion of finally?
So I had a funny experience with that. I was at a conference. Now, I wrote that paper on dark matter wind when I was pretty young, about 23, 24. And this was about 10 years ago. So I was mid-40s, so not...
You're at the conference.
At the conference. Yeah. And one of the people came up to me and said, I thought you were dead.
Oh, God, is that what's going to happen to us now?
You wrote this important paper on dark wind and then disappeared. So that was one of the things that happens when you change fields. Though I now realize, having thinking about this question, I wrote a new paper on dark matter with my friend and colleague Stefan Alexander. So I have in some ways, come back to this.
Lovely symmetry, David.
Yes. And this actually grew out of taking my youngest son on a college visit to Brown. And Stefan and I went out to dinner afterwards. And over some glasses of wine, I started asking some questions about ways in which we can construct models for dark matter, which turned out surprisingly to actually be interesting questions, which we've now written a paper on.
Typical dinner conversation.
Exactly. That's
wonderful. David Spergel, thank you so much for helping us understand the design of the universe, and thank you for joining me today on Design Matters.
Oh, it's a pleasure.
You can find out more about David Spergel at simonsfoundation.org or on the Astrophysical Sciences section of the Princeton University website. This is the 13th year I've been doing Design Matters, and I'd like to thank you for listening. And remember, we can talk about making a difference, we can make a difference, or we can do both. I'm Debbie Millman, and I look forward to talking with you again soon.
For more information about Design Matters or to subscribe to our newsletter, go to debbiemillman.com. If you love this podcast, please consider contributing to our new Drip Kickstarter community. Members get early access to the podcast, transcripts of every interview, invitations to live interviews, Q&A sessions with guests, and a brand new annual magazine. You can learn more about this at d.rip/Debbie-Millman. That's d.rip/Debbie-Millman. If you want others to know about this podcast, please write a review in the iTunes store and link to the podcast on social media. Design Matters is produced by Curtis Fox Productions. The show is published exclusively by DesignObserver.com and recorded live at the School of Visual Arts Masters in Branding program in New York City. The editor-in-chief of Design Matters Media is Zachary Pettit, and the art director is Emily Weiland. Generous support for Design Matters Media is provided by Wix.com.